All right, let's go ahead and get started. So this is going to be lecture number 10, linear estimation and introduction to single path, narrow band, flat fading channels. So let's start off with some motivation for the problem at hand here. So what we've looked at quite extensively so far has been the detection problem. And so in the detection problem, we looked at IAD complex Gaussian noise channels, and the task was to, given this beta, I should write that here too, y then, given the measurement y of n and this beta, to find the best symbol in the finite constellation. And we looked at the best in terms of maximum likelihood detection. So the estimation problem is very similar, except that in the estimation problem, instead of estimating the symbol from a finite constellation, we're actually estimating something like a complex number. For example, we might have the observation y of n, and we might know the symbol that was sent. And then the objective is to find this beta, which is just in this case, a complex number. And so the difference between estimation and detection is really just the size of the set. Detection is there's a finite number of possibilities. Estimation, the values are continuous, real, or complex numbers, or even vectors. And many of the problems that we're going to address now in the course are going to require us to use estimation. Um, and for example, we've already seen how to do the detection problem. We need to have the beta here, which we had taken to be square root of Vx, but in general communication system, the question, of course, is where do you get beta? And where we get beta is we're going to solve an estimation problem. So we're going to be doing this extensively in the next 4 or 5 lectures of the course, really till the end of the course. So the purpose of this lecture is to go through several concepts in estimation. And then if we have time, we'll wrap up with an introduction to narrowband communication systems, and we'll see some of the applications of these impairments here. So let's continue here now. We're going to start off with the area of least squares estimation. And so with least squares estimation, you need to be able to define and compute the least square solution of a linear system. And then I'll explain actually later how this connects back to maximum likelihood. That's going to be actually in the next section here. So I'm just going to delete that. So the least squares problem starts with a system of linear equations. And hopefully you've seen systems of linear equations already, either in your time at UCSD or maybe before UCSD. So a typical linear equation looks like something like follows. There's a matrix A, which is known. There's a vector B, which is also known. And there's a vector X, which is a vector of unknowns. And you can see the dimensions over here. And so people have studied these systems of equations. So each, um, we'll be able to think about this as a set of equations, and then have looked at different approaches for solving to find the unknown vector of x. So what we're going to do is many of the problems that we have in the next parts of the course, we're going to be able to write in the form of a linear system. So I'm just going to put this here, write many estimation problems in this form. So while I'm doing everything here in a generic way, we will see later in the course how to specify the values for each of these vectors or matrices so that it makes sense, of course, in the communication system. But for most of this lecture, we're just going to do something that's very generic. So first of all, let's just get reminded a little bit about what in that linear system, what is AX? Well, if we think about A as being composed of m column vectors, remember that A is n by m, then so it has m column vectors. Each column vector is an n by 1 vector. Then the product of A and X is a linear combination of the columns of A. So the columns of A are A1 through AM, and this linear combination is determined by the weights of the X here. So when I say linear combination, I mean this right here. And then the linear system is saying that AX, this linear combination, should be equal to B. And what we can see is that for there to be an exact solution, it must be possible to find a linear combination, a set of weights of X, such that the linear combination of the columns A equals B. So an exact solution is possible in some cases. For example, if A is square, and we make the assumption that is invertible, then we know from linear algebra that we can write the solution in the following way. So we have AX equals B. We multiply both sides by the matrix inverse on the left, and that gives us the value of X here. So what we're going to be interested in this set of lectures and generally in the course is the case where A is what's called tall and full rank. And essentially what we mean is that A is a matrix where the number of rows is greater than the number of columns, so it's tall. It's like a tall rectangle. And we're going to assume it's full rank, which means that all of the columns are linearly independent. And that linear independence is a concept that you'll see in, other linear algebra courses. Hopefully you've seen that concept already. But basically, this linear independence, we're going to use this fact to later observe that the matrix A conjugate transpose times A is invertible. I'll explain a little bit about this momentarily. So in general, when it's tall, the system is overdetermined because there are more unknowns than there are equations. So it's not necessarily possible to find an exact solution because there's too many things that aren't known. So what we want to do here is to propose to find a solution that is close or is good in some sense. And the notion of good is going to be to minimize the squared error. So this is the 2 norm. It's the sum of the squared entries of the vector. And we're going to find the least squares solution. That's the LS. So least squares as the solution that minimizes the squared error. So squared is there, and this is the error here. So least squares is just the minimizer of the squared error. And we understand that error is the difference between the found value of AX and B. And the achieved minimum error will be AXLS minus B squared will be the minimum error. So let's do a little bit of work here on finding the minimizer. Now, to find the minimizer, we can do this in a couple ways. We can actually write out that squared error as a function of all these scalar variables and use conventional calculus to differentiate with respect to each value of x, put everything back together in a big matrix. What we're going to do is take a shortcut and use matrix calculus. So if you've taken linear algebra, you probably saw some matrix calculus already. You can also look it up online. I'll give a couple of references, a couple pages of background on matrix calculus if you're not familiar. The net of it is that what we do is we differentiate, take the vector derivative with respect to the conjugate of the vector x of that difference here. And so we expand out the sum of the squared error here, and we get these are the four terms, right? Because when we separate this out, we have products of four terms. And when you differentiate with respect to the complex conjugate, it turns out that one of the interesting results is that x and xc are treated as independent. So, I mean, independent in the sense that when we differentiate with respect to x conjugate, the derivative of anything with x in it ends up being zero. So this term here, this is derivative. There's no x conjugate here, that goes to zero. There's no x conjugate here, that goes to zero because of this assumption up here. So I don't mean independent in the statistical sense, independent just meaning they're different variables. And then we're left with these two derivatives here. And to get the second equality, we have to look up something about matrix calculus. But hopefully you can just trust me that I've taken this derivative correctly, and this is the result of that derivative. So we're going to set that equal to zero. This is a quadratic equation. So we know if we take the derivative, we set it to zero, we're going to find in this case here, the minimizer. And so we set it equal to zero and we simplify. So what I've done here when I'm setting it equal to zero, I'm just showing you that here, this is the error. Right here is the error. And then that error times A conjugate transpose is equal to zero. This is called the orthogonality condition. And so if we remember of A as being composed of these column vectors through AM, what this says that is that every column of A, let's call it A sub k, is orthogonal to the error for, I should put the LS here, for the least squares solution. So the least square solution has this interesting orthogonality property that the error, what we say is the error is orthogonal to the data, or the error is orthogonal to this, the vectors here in that make up the A matrix. Now, simplifying that equation, so moving the B to the right-hand side, we get what are called the normal equations. And so in linear systems theory, both orthogonality condition and normal equations have very specific meanings. And so I don't mean normal like Gaussian. This is just called the normal equations in linear systems here. So the normal equation is saying that XLS is related to B in the following way. Now, because I've assumed that the A is full rank, A star A, which is M by M, is a square matrix and it's invertible. And it kind of makes sense because we've gone from A star, A conjugate transpose A, we have a fat matrix times a tall matrix. And so we've like made that big matrix more like a small square one. And that linear independence of the columns that gives us invertibility so we can write that the least squares solution is A conjugate transpose A inverse A conjugate B. And the squared error, we just substitute in that value for the least square solution into the squared error and simplify. And because of the orthogonality condition, we ends up, so this goes to zero because of orthogonality. And so then we're left with this product here, which becomes B conjugate transpose B minus B conjugate A XLS. And this is a way that we're measuring the performance of the estimator. And if that squared error was zero, it would mean that that we're able to find a very good value of x. And if that squared error is large, it means that the solution we found is the best of all of them that we could find in the squared error sense, but it didn't match very well. So without getting any questions here virtually, I'm going a little bit fast, but I'll try to pause here and think about the geometric interpretation. So let's look at the collection of possible vectors that can be created by any linear combination of the columns of A. So remember that this product is the sum of those m columns times the coefficients of m. And so we can think about the coefficients of m. This is for every possible value of x is called the span. It's the space created by all the linear combinations of x. And this is an example of, this example corresponds to m equals 2 and n equals 3. It's really the only example that we can easily illustrate in real, of course. And so all the linear combinations of A, they have to live in this plane, which is a subspace of the three-dimensional space. And we have a vector B that lives in the three-dimensional space. So it's in 3 dimensions. And we cannot find any point in this plane that exactly matches B because B is living outside of that plane. So what the least square solution does is the least square solution says, okay, so the error between the least square solution and the vector B satisfies orthogonality. So what does that mean here? What that means is that this error vector is orthogonal to this XLS. And so how we see the orthogonality is, remember that XLS conjugate transpose, A conjugate transpose, A XLS minus B. And remember that this here being 0 was the orthogonality condition here. So the least square solution is the point where you get what's called an orthogonal projection from the vector B. It's the point that is the closest, has the minimum distance to B. And it turns out that this quantity here, A star A inverse A, is the projection of B onto the space spanning A, and that is just keeping in mind what XLS is, that's just A times A star A inverse A conjugate B, which is just XLS. So I'm just trying to show you that it's all the notation here matches. And then that error is a projection of B onto the orthogonal complement of the rows. That's something we don't necessarily need. What I would say is to focus on this picture here and try to understand this picture in the context of the least squares algorithm. And that's something that I would say if you haven't taken linear algebra, to spend a little bit of time on this. You can certainly find many examples online where they explain this well. So that's the geometric interpretation of least squares. So let me provide a summary here. So least squares, in machine learning, this is called linear regression or least squares regression. is a basic approach for solving an overdetermined system because we can't guarantee we get an exact solution. So we come up with a cost function and find the solution that minimizes that cost. And here the cost is the squared error. So there's adaptive versions of least squares. So something called recursive least squares, where you can actually implement least squares in the case where the matrix A is actually growing. So we keep getting rows, another row, another row, another row, another row. So imagine A is getting taller and taller and taller. And it's possible to update the least square solution for if we add one new row as some function of the least square solution for m rows, and then continuing here. Sorry, n should be n plus 1 and n. So that's the subject. If you take adaptive filtering, you would study this concept a lot more. So the suitability of least squares, I mean, we have to have a model that we believe is described by a linear system. So we have to be able to find an A such that AX equals B is somehow meaningful, right? So you can't use it in every problem, but you can use it in a wide variety of problems in communication systems. And we're, for the most part, going to use least squares estimators. They're not necessarily the best estimators, but they're very low complexity to compute. They don't make any assumptions about the distributions of any of the quantities here. So it's all just completely deterministic and based on linear algebra. And so we'll use these in a lot of the course. But there are better estimators. And so I want to tell you a little bit more about some of the other estimators and how they connect to least squares. So the next one we're going to look at is maximum likelihood estimation. And as I made this joke today in the class on Thursday, that ML before your time, ML always meant maximum likelihood. I mean, any paper you saw ML in, it was just assumed. And nowadays, if you see ML in a paper and it's not defined, it's just assumed that it's machine learning. So things have changed. But for me, ML is normally maximum likelihood. So now we're gonna formulate and solve an estimation problem that's very similar to the detection problem that we solve based on likelihood functions. So to do this, we're going to introduce a little bit of probability here in the model. So let's look at a basic linear estimation problem where we have y and a and x, but now we've got that unknown value of v. Should a is also known here. And so V you can think about as being like measurement noise or additive Gaussian noise. Let's suppose that it's IAD, zero mean and unit variance. It doesn't have to be unit variance here. If it's zero mean and unit variance, and we're going to use the maximum likelihood approach to estimate X given A and of course Y. So it turns out that the likelihood function, it's possible to generalize the likelihood function of the complex Gaussian distribution that we've been studying to the multivariate complex Gaussian. And you can find out more information about this online. There's some information about this in the book. The normal, complex normal, zero mean, IID random vector process, complex Gaussian is zero mean, and then this is the correlation function, expectation of V conjugate transpose equals identity. Because it's IID, each of those entries is uncorrelated, and then it has unit variance because I just assumed that the variance here was 1. And so this is the likelihood function here. So the likelihood function, so conditioning on x being known, so we condition on a is known, x is known, then this becomes complex normal with mean a of x bar here, and variance is still the covariance is still identity. So this becomes the likelihood function that we want to maximize. And this is related to the multivariate Gaussian distribution. And so notice that this looks right here a lot like the error that we saw in least squares. And so this likelihood function has some similarity with least squares. And so hopefully what you can see here is that maximizing the likelihood, well, you have to minimize the argument of the exponential. So it's basically the same. So in this particular case, the maximum likelihood estimator with IID Gaussian noise actually gives us the least squares solution as well. So the least squares has an extra degree of optimality. It's also the maximum likelihood estimator under some assumptions. So that also means it's a good estimator in a statistical sense, not just in a deterministic sense. So this is ML estimation, not detection, because the unknown vector is in Euclidean space. So again, the unknown vector x lives in general in this complex n by 1 space. The least square solution has some optimality from an estimation theory perspective, but that optimality really does hinge on IID Gaussian noise. If you have another kind of noise, it's correlated, anything else, then the maximum likelihood estimator is not going to be optimum anymore. So the maximum likelihood estimator is optimum, but the least squares is not the maximum likelihood estimator. Now, another thing to note is that the maximum likelihood estimator doesn't use any prior information about A or X. So it's still treating them in a deterministic fashion. It's not exploiting any probabilistic model about either A or X. So now let's look at another approach that's going to relax this a little bit. So let's look at now the minimum mean squared error estimator. So to do that, let me just 1 second here. So let's continue now with another estimator called the minimum mean squared error estimator. So here's the minimum mean squared error estimation principle here. So let's suppose that we have two vectors, x and y, of different dimensions, and that they're random vectors. And the conditional distribution of f of y given x is known. So the minimum mean squared error estimation principle is that given y, let's find an estimate, x hat, which is a function of y, that minimizes the mean squared error. So this is the error squared, and the expectation here gives us the mean. So what we want to do is we want to find a function, it could be a nonlinear function, that maps the observation of y and find something that's close to x. So this is a little bit of a different problem than we've seen before. So we have a function here that's unknown. And we've also got an expectation too. And that's where the statistical assumptions come in. So without going through all of the derivations, it turns out that for the minimum mean squared error estimator, there's a closed form solution for that optimizing function. And that's called the conditional expectation. So the actual function itself is the expectation of x given y. And this function satisfies the property that the average error conditioned on y is equal to 0. And it kind of makes sense because this conditional expectation makes sense to work with the conditional expectation because we have the value of y and we have that conditional knowledge of this conditional distribution, but we also need to know, well, I'll show you here, but we need to know f of x and f of y as well, which I should have mentioned here. So let me explain a couple things about MMSE estimator. So how do you compute the MMSE estimate? Well, you have to compute that conditional expected value. So we observe a value of y, which would be, say, y0. So we compute the expectation. So we integrate the conditional probability distribution function here. let's call that, I was usually using F here. So we integrate that distribution. This is our conditional distribution. This is f of x given y. And this is the distribution of f of y given x. That's the distribution of x there, which we also need to have. And so computing that conditional estimate involves somehow computing um, these integrals here, these expectations here. And this normalization down here, this is so this down here is a scalar value. So the math of this works here, the division. So the MMSE estimator satisfies an interesting property. It has an orthogonality condition too. The error, remember this is the error here, is orthogonal to any function of the data, y, which is kind of interesting here. So it means that if you make any vector function of y, then this average value is zero. That's orthogonality condition. And what the orthogonality condition, what it says in a different way is that the expectation between x and g of y for any g is equal to the expectation of x minus that conditional expectation plus the expectation of g minus that conditional expectation. And of course, how we can make this function here, because both of these are positive, we can make this zero if they're the same. So that's part of how the derivation works. You don't need to know how to do the derivation, but I wanted to give a little bit of background here. So a little bit of discussion about this. I mean, we need to have really this joint distribution to make any of this work. Um, this is a very general approach because it can capture any kind of distortions, nonlinearities, impairments. So this is a very, very powerful approach. But the problem is you really need to have models that explain how to get, this joint distribution. And so nowadays it's been popular to use data-driven approaches. So now we're looking at machine learning, not maximum likelihood, to learn that conditional expected that estimator from the data. So there's people that have been writing papers where they train a neural network to try to learn that conditional expected value estimator to learn that function, that optimum function. Um, so there's a lot of recent research on that, much of it related to communications. And then there's also approaches that are called Bayesian methods that generalize MMSE by instead of just finding a function that does an estimation, it actually tries to find a probability distribution function. So imagine instead of getting the average value of x, you get that distribution itself. And so Bayesian methods learn that distribution from the data. So MMSE is very powerful, and it might be useful in your future work or your future research, but MMSE is often is not computationally tractable, and it also requires making a lot of assumptions about probability that maybe we don't know how to do in practice here. So I'm going to conclude this discussion of estimation by introducing the linear minimum mean squared error estimator. And this is related to the MMSE as a special case of it, in fact. So linear minimum mean squared error estimation, we're going to assume that the estimator x hat is a linear combination of the observations of y. And for convenience, we're going to put conjugate transpose here. And that G LMSE minimizes the average error between x and y. So this is the error. Looks a little bit like least squares, not the same though. And then there's the average there, here, the expectation. So the MMSE estimator finds a function of y. Here we have a linear function. So we're specifying that it has to be linear. And then the minimum mean squared error problem in general is finding the function that minimizes that expected value. Whereas here, we're finding the weights of a linear combination of a matrix that minimizes that value. And that function in the MMSE case is the conditional expectation. And in the LMMSE case, well, we need to see what that is now. So let's look at how that works. So let's derive the estimator here. So I'm going to take, we could do this in a vector form, but I'm going to show you how we can derive it in perhaps slightly easier way here. So x minus g conjugate of y, this is our error here. So I'm going to break up that error as a function of x1 minus g1 conjugate y. So g1 is, so we have g, these are the columns of g. And since we're taking G conjugate transpose, those columns become row. These becomes inner products here. And we're looking at the expectation of the squared error. So the error, each of these terms is an error that's being squared. And we're going to sum all of the squared errors. And because we have m different G vectors, when we minimize this, we can minimize with respect to one of the values of G, and then the other ones are zero. So we take the derivative of this, like in the approach that we use for least squares with respect to the conjugate value of G. So we can get rid of the sums. Now what we're going to do is we're going to expand that magnitude there. So the absolute value can always be written as the product of a conjugate scalar and the scalar itself. We multiply those two out, just like we did with least squares. And then we take the derivative here. So we're going to expand the squared magnitude. Um, so I should say what we're doing here is we're swapping the order of the expectation and the derivative. You can actually do this without doing that, but it just for convenience, it's easier to show like this. So we've taken the derivative of this here, and just like before, several of these terms get canceled because they're not a function of the conjugate of gk. So we take the derivative. I should put the c here. And then in the same way as before, we end up with something that looks like gk y minus x of k here. So this is the error again, and that's the observation. So now we take that expectation and set it equal to 0, and this gives us the orthogonality condition for the LMMSE, which says that the error is orthogonal to the data of the observation y. And so rearranging, setting this equal to 0, rearranging, taking the expectation, we get the condition that RYY, which is the autocorrelation of y times g, is equal to RYX of k. So what I mean here by x is this I mean is exactly the expectation of y with the kth entry of x, is what that is here. So this is what that means. And so now if I take all the columns of G and put them together into a matrix, then I can rewrite this as, and then I'm getting all the columns of Ry of x, and then I multiply by the inverse, I get Ryy inverse Ryx. So this is the LMMSE solution here. Quite famous that the least squares LMSE estimator. Now you might have seen this in a slightly different way, but remember we had the conjugate. So our XLMMSE is equal to G conjugate LMMSE of Y, which is going to be equal to RYX conjugate transpose RYY Hermitian times Y. So the way we think about this here is that this covariance here, we're taking the inverse. We're like decorrelating y somehow. And then this right here, we're connecting y back to x. Because Ryx is a covariance matrix, it turns out that this is equal to xy. So you also see this written as Rxy, Ryy inverse y. And then here's the squared error expression. So we can plug in the error and look at the error covariance matrix, which is called E, and expanding that out and exploiting the orthogonality condition, we get that the error covariance is Rxx, G conjugate transpose Ryx, and the resulting squared error is just the diagonal terms of that matrix here, and that's what the trace does. So the trace sums elements on the diagonal. So that's just the expression for the squared error here. Okay, so now to move on, let me try to just summarize by connecting all of the estimators together. So we're going to look at a particular example and try to see how each of these different estimators looks. So here's a canonical estimation problem. Let's suppose that we have y equals ax plus v, y is the n by 1 observation, m is our unknown vector to be estimated, v is modeling the noise, and a is a known model parameter. We're going to suppose that a is tall and full rank. So this looks a lot like the maximum likelihood estimation setup here. But I didn't say anything yet about the noise distribution. So let's see, what does the least square solution of this problem look like? Well, the least square solution just ignores the noise and plugs it in. So this is our least square solution. What about the maximum likelihood solution? Well, to find the maximum likelihood solution, we need to make an assumption about the noise. So let's suppose that the noise is correlated Gaussian noise. And it turns out that the correlated noise distribution has a probability distribution function that looks like this. This is the determinant here. And then this is the noise covariance matrix, and it shows up in the inverse there. And so the maximum likelihood solution finds the x that minimizes this quantity here. And if the noise is IID, we get exactly the solution that we saw before, which is the least squares solution here. So I didn't give you the derivation for the correlated case, but you can see that if you follow the same logic as what we did before, that this will be the solution. So the maximum likelihood generally is different. If the noise is IID and Gaussian, then it's the same as least squares in this problem. Now let's look at the LMMSE solution. So we're going to suppose that X and V are uncorrelated. They're both zero mean, and they both have known covariances here and a cross covariance. And they're uncorrelated, so the cross covariance is zero. And we're not going to make any Gaussian assumption. We're only making assumptions about the first and second order statistics. Then we can compute Rxy based on the linear model, and Rxy is equal to Rxx A conjugate transpose here. And then Ryy, computing this and exploiting uncorrelated property, then we get this up here. And then we can plug in and get the LMMSE estimator by inserting those values. And then we can substitute in the quantities that we just derived into that estimator here. And then I want to note that both of these values here are the same, but you can get them by using what's called the matrix inversion lemma and some linear algebra. It's beyond the scope of the course, but I just wanted to show this to you because it is one of the classic um, applications of the matrix inversion lemma in minimum mean squared error estimation. And you'll see this in books in one of the two forms. Um, so the net of it is that we can find LMMSE solution in the following way. Now, so I'll come back to this in a moment here. Now let's look at the MMSE solution. So now let's also suppose that X and V are Gaussian, which we didn't make the assumption before. Then it turns out that y equals ax plus v is Gaussian, and that x and y are jointly Gaussian. And furthermore, the conditional distribution of x and y is Gaussian with this um, distribution function, which we did not cover. And then it turns out in this case that the MMSE estimator is actually the LMMSE estimator here. So this is a case where LMMSE and MMSE is the same. So you can see like kind of a common theme here, right? If things are Gaussian, then we start to make connections between these different estimators. Let's go even further here. Let's suppose that the noise is that we have IAD noise and that we have an IID assumption about RXX here. So then the LMSE estimator looks like this. We substitute in for the values of correlation here. And then this quantity right here, this is just SNR inverse. And then if you compare this with the least square solution, remember the least square solution was A star A inverse A star Y. That was X. That was the least squares here. So we get that, so the MMSE, the LMMSE are the same. And then this looks a lot like least squares, in fact, except that the difference with the least squares is we have this regularization. So we have an inverse here of A conjugate A, and this little perturbation by identity, it makes this more invertible. And so it's kind of interesting that we can look at these two cases here. Let me write them over here. So low SNR, then sigma v squared over sigma x squared I plus A conjugate A inverse. If low SNR is small, then inverse SNR is big. And so then this actually converges to an identity, and the least square solution converges to A star Y, which is a matched filter. And if there's high SNR, then it actually converges to A conjugate transpose A inverse A conjugate Y. So at low SNR, it looks like a matched filter, and at high SNR, it looks like um, the least square solution. And so the linear minimum mean squared error solution has this kind of trade-off that in this Gaussian channel that at low SNR, it's a little more robust, and at high SNR, it's like least squares. And then now we have this solution here. I want to go through, this is a special case where A is a vector, X is a scalar, and V is unknown. So we can go through and solve all of these different special cases here. So XLS is a scalar, and that's just going to be A conjugate transpose Y. Sorry, let me erase that here. So that's going to be A conjugate A inverse A conjugate transpose Y. But because these are vectors, A conjugate transpose A is a scalar. And so, sorry, that should be inverse here. So this is going to be A conjugate transpose Y divided by the norm of A here. And we can write this out as in, in, in terms of actual computation here as like n equal 0 to n minus 1, A of n conjugate y of n divided by sum. So it has a very simple estimator. And then because it's uncorrelated, this is also equal to, and then this is Gaussian. This is also the ML solution. And then the L MMSE estimator we can get from the previous slide here is just going to be sigma v squared over sigma x squared plus a star a, which is again that a star a inverse here, a star y. And so if we were to write this out, this would be like sum from 0 to n minus 1, an conjugate yn divided by sigma v squared over sigma x squared plus the sum from n equals 0 to n minus 1, a of n squared. And so you can see in this example here, like we're regularizing that inverse based on the SNR and changing the estimate. So the least squares and linear minimum mean squared error estimator, even in this case, won't be the same unless this value of inverse SNR goes to infinity, that term goes to 0. And we're going to use this estimator quite a bit later in the course here, in the next, starting next week. Okay, so I have a bit of time left, so I'm going to go through now the final part of this lecture, which is the overview of challenges of single path communication channels. So I'm going to start by explaining, okay, so what is a single path wireless channel? So we have to go back and think from when we did the complex baseband equivalent channel several lectures ago. So remember, we went through this derivation of what is the channel, the passband channel, deriving its baseband equivalent, then sampling it here. So suppose we have a single path channel. So this just corresponds to, we can imagine an antenna at the transmitter and receiver, and there's some delay and attenuation. That's it. It's one path, and we can model the impulse response of this one path channel as an attenuation times a delta function that corresponds to the delay. So if we go through the derivation for the complex baseband equivalent, and there's an example of this in the slides and examples in the book, we find that the equivalent baseband channel looks like as follows here. So there's a term here that depends on the bandwidth. There's a sinc function with a delay. There's our scaling alpha, and there are e to the minus j 2 pi fc times the tau of d here. So the alpha shows up here. The delay shows up both here, and then we're picking up the carrier frequency as well. And if we look at this in the frequency domain, we take the Fourier transform. Well, it's just because we have a sinc function, we just have a rectangle. I mean, we have a magnitude and the phase. The phase depends on the value of tau of d, but the magnitude doesn't depend on tau of d here. So this will be like this phase slope here is the argument of the e to the minus j 2 pi fc of tau d. So such a channel is often called a narrowband channel because, so suppose that we just have an arbitrary frequency selective channel. So that h of c is just some frequency selective transfer function. If we have a wide bandwidth, when we take a piece of this channel, we see the curve here, right? We see a substantial amount of curve. But if we look at a very narrow bandwidth, that slope is very small. And so if we expand then, we zoom that out, and we're trying to show this here, we go to zoom it here, then it looks approximately flat. So for very narrow bandwidths, any frequency response will basically look flat. And such channels are called approximately flat or called frequency flat or narrowband. So single path, frequency flat, and narrowband all mean something very similar from a modeling perspective. So the next couple lectures, we're going to focus on communication systems that have a narrowband communication channel. So in particular, we're going to consider the following. We've got our complex pulse amplitude modulation. So we're generating bits, converting them to symbols, doing the pulse shaping, generating complex baseband signal X of t. It gets launched in the propagation environment so that X is convolved with the channel and then is up converted, convolved with the channel, down converted, and then sampled. So this is just exactly our architecture as before. The main thing that we're introducing now is we're introducing a channel here that is more complicated than just the square root of EX that we had before. So let's look at how we can look at this here. So if we convolve our X sub t with our complex baseband equivalent channel, well, we've got, remember that H of t, right? So the H of t was at the complex baseband was alpha e to the minus j. I should have a minus there. 2 pi fc of tau. And then there was like a b sync of, let me go back over here to see what it was here. Um, b sync of b t minus tau d. But this here is part of the unit gain low pass filters, that sync function here. So we could write this as alpha e to the minus j 2 pi fc of tau d convolve with b sync b of t, which is just the ideal low pass filter. And since our communication signal is also a low pass filter, we can throw that sync function away and we're just left with the tau d. So I forgot the delta of t minus tau d here. So when we convolve with the channel, the complex pulse amplitude modulated signal here, note that it doesn't convolve the noise. Then we pick up the square root of Ex times alpha times e to the minus j 2 pi f sub c of d times the sum of our complex pulse amplitudes, and we picked up a little delay here. So we've got now, so going back over here, using the pink here. So you can see that the delay shows up here. The alpha is here, and then we also end up with the delay times the carrier there. So we're going to combine these square root of Ex, the alpha, and that complex phase shift. We're just going to combine that together into a complex number that we're going to call the narrowband channel. It's a complex number. That's going to be our flat channel. And then we're going to account for the delay explicitly as it affects the pulse shape here. Now the delay is also in the channel, but unless we're solving something like a radar type of a problem, we normally just consider the combined effect of the delay and the carrier just as an arbitrary phase shift, and we just treat that as a complex number. So we don't exploit that delay, that structure here. So this whole story here was at baseband, but we can go a little bit further. Remember that the baseband signal, the complex baseband signal, is converted to passband. So here's a quick refresher here. So the complex baseband signal, these are the samples that we derived a couple lectures ago, the samples of that baseband waveform here. This is the in phase, this is the quadrature parts, or the real and imaginary parts. Each of those is converted to continuous time, and then the in phase part is multiplied by a cosine, the quadrature part multiplied by a sine. These are added together, and that's our passband communication signal. And then at the receiver, the process is done in reverse. We multiply by a cosine and a sine, we low pass filter and convert a continuous to discrete converter. Now the issue is that the cosine and sine, they're generated from an oscillator. And the oscillator is like a quartz crystal, is vibrating very fast, is used as a reference. But the oscillator at the transmitter and receiver aren't exactly the same. They can differ by kilohertz, very small amounts, but they still differ a little bit. And so we end up with a slight difference between the carrier at the transmitter and the carrier at the receiver, and that's shown with this prime here. This is called carrier frequency offset. So the offset is that the frequency used at the receiver is not the same as the frequency used at the transmitter. And this has a big effect on the received signal. So let's look at how we model it here. So we can go through the math and show if we have an error, then we can model that error. So here's the passband receive signal multiplied by the cosine of FC of prime. And then we just have to use the trig identities and the filtering to remember that. So we multiply through, we have this sum angle formula here. We do the same thing with the passband of the quadrature part, and then we filter. We get rid of the parts here that are related to the let me see here, 2 pi sub c t. Yeah, I forgot there should be a factor of, this should be 4 here because we had part of this gets double the frequency here. So when we low pass filter, we're going to X these and we end up with effectively a signal that looks like r prime of t is e to the j 2 pi f e of t times r of t here. So it's kind of like having, this is our r of t is our complex baseband input signal is multiplied by a little complex exponential. And FE is the carrier frequency offset, and correcting FE is known as carrier frequency synchronization. So if we put it together, a reasonable model for our complex baseband signal here, sorry, I forgot the T there. So it should be T minus tau D here, this is our complex baseband receive signal before the match filtering. And it's got a contribution due to carrier frequency offset, a contribution due to the channel, and it's got an effect of the delay here. And then furthermore, we can make an assumption that the offset is very small, so that when you do the filtering, the match filtering, we can, and the match filter is not too many taps, we can actually just model this equivalently as if the carrier frequency offset applied after the matched filtering here. So so basically what we're saying is that we can pretend that the offset happened after the filtering, even though we know, of course, that the offset was there before. And you can derive this using Fourier theory, a little bit more complicated. We don't need to do it. So after sampling, we end up with the following system model. So we're going to end up with the carrier frequency offset, this epsilon zero is that error times the symbol period t. And that offset isn't known to the receiver because if it knew it, it would just correct the clock. So it doesn't know it. It doesn't know the channel H, and it doesn't know the delay. And of course, there's still noise there. So what's happened is we've introduced a whole bunch more impairments now in our received signal that need to somehow be incorporated so that we can detect the symbols that were sent reliably. So the last few slides, I'll just give you some examples of, so what we're going to do is we're going to look at each impairment in isolation. So neglecting the other one. So you get some intuition here. So first of all, the symbol timing offset. So what if the receiver doesn't sample quite at the right point? Well, if that's the case, then remember when we did the derivation of the Nyquist pulse shape, that required that the pulse was sampled at the right point. Otherwise, you get intersymbol interference. And so when you don't sample at the right point, you lose some gain on the desired symbol and you pick up residual intersymbol interference. So, for example, I mean, these are the places that should have been sampled, and then the places that are actually sampled. So if you sample off, you can see that instead of being here, the symbol value is here. So it's more likely that noise pushes that detection to make an incorrect decision. So when the sample timing is offset, the intersymbol interference creates detection errors. And so we're going to implement something called symbol timing to resample the signal so that it's sampled at the right point. Now, what if the offsets are large, like multiples of a symbol period? Well, if they're large, then we can think that the received signal is just a delayed version of the transmitted symbol sequence, but the offset is unknown. So we don't know where the symbol sequence starts. And of course, when you're decoding your data, you need to know, where the data is. This is called frame synchronization problem. And so we're going to use an algorithm to find the starting point essentially for our data to estimate the difference, to estimate this offset. What about the channel? So neglecting noise, neglecting everything else. Well, that channel is a complex number. So what it does is it takes, for example, our 4QAM, so this is 4QAM, and it rotates it. So it rotates and scales because it's a complex number. So it can squish it, shift it. And so when you make it, if it rotates and squishes just a little bit too much, then the constellation gets completely rotated. And so all the detection errors will be gone. I mean, we cannot implement the ML detector of y minus h s of n if H is not known, right? So you can't do the detection correctly. So we need to know the H. So we're going to develop an estimator to estimate that H, and then we're going to equalize that by dividing it out or using it as part of the detection. And we're going to use least squares estimation for that. And finally, let's look at the carrier frequency offset. So the effect of the carrier frequency offset is it's creating a little bit of a rotation, right? So it's multiplying our symbols. So it's making our constellation rotate, rotate, rotate. And so as time goes on, the constellation effectively rotates completely out of the original Voronoi regions, and all the detection results basically become an error. So what we're going to do to solve this problem is we're going to estimate the epsilon, and then we're going to derotate it, right? So derotating is basically going to be multiplying by e to the minus j 2 pi epsilon 0 hat of n. So we're going to estimate epsilon and derotate it out. Now, of course, what I've shown you is the effect of each of these impairments separately, but naturally they all come together. And so we need a set of algorithms that deal with all of them at once. And so we need to be able to correct for the timing, the frame, the channel, and the carrier all together. And so this is going to be the subject of the next lecture on Thursday, and it's also going to be the topic that we explore in the next lab to develop algorithms for estimating these quantities and correcting them, and then realizing how they work on the actual system. Now, the key to doing that is going to be the following. So we're going to leverage known signals called training or pilots. So this is going to be known information that we can use to find these things that are unknown. And so, for example, in communication systems, what we do in our experiments, our lab, our simulations, is we actually have a communication system where there's a payload of data and a training sequence that's known to the transmitter and receiver. And so what happens under the hood in the MATLAB functions is that there's algorithms that find that training sequence and estimate these unknown parameters. and that's what we're going to be implementing later. But in the lab you're doing for this week, that's due Wednesday, all of that is already working. You don't have to build that here. So we're going to be using the training and the pilots. And then just as a comment that, we're going to be using what are called burst mode approaches where we acquire the data and we do the processing. There's also adaptive approaches that can be even better, but we're not going to pursue those in the course here.